so let's finally write a half reaction. Let's do the half that is reduction first. So that half reaction. So I decided who got reduced, who went down. H. H went from being +1 to 0. So that's what I do. I just write H. Once upon a time, H was +1, and it became H with a 0 charge. I'm not going to put the 2 out in front, and I'm not going to put this little 2. I could, but then I'd have to like balance those, and it gets kind of annoying. So it's easier if you just strip them of all those numbers, like this 2 out in front, get rid of it. This 2 down here, get rid of it. It would balance out, but you'd have to balance it, and it can be annoying. Or sometimes it isn't, but let's just not do it. So I'm just taking the letter and the charge. H, once upon a time, H was +1, and then after its change, it became 0. And then the annoying thing you have to add here is you have to show what the electrons did. So you can either say, okay, reduction is gain of electrons. So this, I'm going to show the electrons on the left-hand side. I'm going to show that one electron on the left-hand side to show that it was gained. The other way I can figure out, it's basically just hard to figure out which side the electrons go on. So the other way I can figure it out is to go, okay, well, both the sides are supposed to add up to the same charge. So right now this is +1, this is 0. So so if I add the electron to this side, I've got +1 and a -1. So that side equals 0, this side equals 0. If I had added it over here, now this side I'd have a -1, and this side would be a +1. And those are not equal. But when I put the negative electron over here, now I have one negative thing and one positive thing, so my charge adds up to 0. Over here, I have one negative thing and a 0. Oh, wait a minute. Oh, so, wait a minute. Okay, so that's why you don't do that, because that doesn't work. I confused myself. All right, so I have, over here I have +1 plus a negative electron adds up to 0, and then over here I just have a 0. So it's not that they have to add up to 0, it's that they have to equal each other so that you show conservation of charge. All right, let's look at a little harder one. If you were writing one for iron, you said once upon a time iron was 3+, and it became just regular old iron with a 0 charge. It looks like there was a change of 3 electrons. Where do I put it? So 2 ways to figure it out. Both are kind of hard, I guess. I can either say, okay, well, this is reduction. The charge got reduced down from +3 to 0. Reduction is gain, if I want to like really understand what's happening. So, okay, I'm going to show the electrons being gained over here. Because when they're over here, that's kind of like they were given off. When they're on the left, they're gained. So I can say, okay, I'm going to put the 3 electrons over here because reduction is gain. Or I could say, well, I'm trying to make both sides add up to the same number. So right now, this side adds up to 0, and this side adds up to +3. So why don't I add 3 negative things so that now this side adds up to 0, both sides add up to 0, and now my 2 sides equal each other, showing conservation of charge. Check. Okay, let's look at one example of oxidation. So this one shows an opposite example where once upon a time Fe was 0 and it became Fe with a 3+ charge. So again, it looks like there's a change in 3 electrons, but where do I put those 3 electrons? Were they lost? Were they gained? Did they go on the left? Did they go on the right? So if I were to put them over here, +3 negative electrons, then this side would add up to -3, and this side is a +3. So that's not right. I'm not going to do that. So let me put them over here. And now I have 3 negative things and 3 positives. So this side equals 0, this side equals 0. Okay, that was the right thing to do. Got it. I can also say oxidation oil. Oxidation is loss. And if I show the electrons over here, I'm showing them being lost. I'm saying I had Fe, and now I have Fe that's missing 3 electrons plus the 3 electrons that are now separate from it. All right, so again, you're just going to write what it was before, now what it is after, and then you got to decide which side to put the electrons on. You can decide either by saying, oh, if they're gained, they're over here. If they're lost, they're over here. Or you can say, I'm going to put them on whatever side makes it so both sides add up to 0. All right, let's do one big example problem. So here it is right here. And the first thing I have to do to approach these redox problems is assign oxidation numbers. So that's why you want to be good at it. So Mg, if I go to look it up, oh wait, it's alone, so it's a 0. Zn, if I go to look it up, it has multiple possible charges. So I go over to chlorine. It's only negative choice. I need it to be negative. It is -1. So I'm like, oh, zinc must be +1, right? Oh, wait, no, there's 2 of them. So that's 2 negative ones is -2. So I need zinc to be +2, because remember, the whole point is for this whole compound right here, just this little piece, to add up to 0. Okay, right here, Mg, if I look it up, is always +2. Cl is -1, and I'm like, oh, that doesn't add up. Oh, wait, yes, it does, because there's 2 of those. So that would make +2. That would make this -2, +2, adds up to 0. Zinc, I go to look it up, and then I'm like, oh, wait, no, it's by itself, so it is a 0. All right, now I can identify who got oxidized and who got reduced. So who got oxidized up? What did you do, Mg? You went from being 0 to +2. Okay, so it was Mg. I just picked the first thing I was looking at. So Mg got oxidized. So when I write the oxidation half reaction, I will tell the story of Mg. So I'm going to say, okay, Mg, all I'm going to do is say Mg was 0, and I'm going to leave a little space because I don't know where the electrons go yet. And now Mg is +2. All right, and now I can either say, okay, oxidation is gain, oil rig. Oxidation is loss, oil rig. So I should show them over here, just show the electrons being lost. Or I can just say, well, I need it to add up to 0. By the way, let's see, I went from 0 to +2, so there's a change in 2 electrons. So I'm going to put 2 electrons over here. And I can either say I'm putting them there because oxidation is loss, and when you put them on the right, you're showing them being lost, like given away, whereas over here they'd be like added. Or I can say, well, I'm trying to get the whole thing to add up, both sides add up to the same thing. So this side adds up to 0, this side's +2 and a -2, so this side's 0, so I did it right. So there is my oxidation half reaction. It's called the half reaction because I'm only telling one half of redox. I'm just saying the ox part of redox. So let's do the red part of reduction, oxidation reduction. Let's do the reduction half reaction. So who got reduced? Let's see. Cl went from being -1 to -1, so it wasn't Cl. Zinc went from being +2 to 0. Okay, so zinc went down. Zinc, and so all the half reaction is I'm just going to tell that story. I'm going to say, okay, once upon a time, zinc was +2. And I know that because I assigned all the charges ahead of time. And then it became, what's it over here? Oh, it became 0. Right, so just telling the story. And then it looks like there was a change of 2 electrons. So where did they go? Let's see. I'm going to put them on the left, either because reduction is gain, and when you put stuff on the left, you're showing it being added. Or because I know that adding 2 negative things over here with this +2 would make this side up to 0, this side 0, and so the 2 sides add up, showing conservation of charge. Another thing now showing conservation of charge that you might notice is that you can see zinc gained 2 electrons and magnesium lost 2 electrons. And that's how redox works. One thing loses, the other one gains. It's not like one thing loses and it just goes and disappears into nowhere land, right? Because we're showing conservation. Nothing is created or destroyed, just this thing loses and this thing gains those same number of electrons. So that could maybe be a question. If one thing loses 2 electrons, how many does the other gain? Well, if this one lost 2 electrons, this one will gain 2. Okay, let's do one more example. If you get it, you can do it on your own. But the first thing to start this problem, I'm going to assign charges. And again, copper, I go to look it up and then I remember, oh, if it's alone, it's a 0. Next one, AgNO3. So Ag is +1. And if I look it up, it has a whole bunch of choices, so I'm going to skip it. That usually happens with the middle element if there's 3. And O is -2. But there's 3 of them, so that adds up to -6. So Ag is +1. O adds up to -6. So what does N have to be so that this whole thing adds up to 0? 1 plus what? -6 equals 0. Well, I usually want like the pluses to add up to the same as the negatives. So if I have a +5 here, I'll make this a +5. Then it'd be like 1 plus 5 is +6 -6 equals 0. All right, so you're trying to make everything equal 0. Okay, next one. Cu has multiple possible charges. NO3, annoyingly, is a little thing in parentheses. You can go look it up on table E and see that this whole chunk is -1, there is 2 of that whole chunk, so that means that whole chunk is -2, which means that Cu part must be +2. Kind of annoying. And then Ag, I'm like, oh, I remember that was +1 from over here. No, it's 0 because it's alone. It hasn't bonded with anyone, hasn't lost or gained electrons. So just rewrote that a little bit neater. But I do need to figure out what this N is. I got that Cu is +2. So if this whole chunk here adds up to -1, and the O is -2, I need this. Oh, this is so annoying. I hope you don't get this on the region. Well, you don't have a regions. So 3 -2s makes -6. So N, to get the whole thing to equal -1, it would have to be +5. All right, who got oxidized and who got reduced? Cu, what did you do? You went from being 0 to +2. So you went up. So it got oxidized up. Who got reduced? Let's see. N went from being +5 to +5. Nope. O went from being -2 to -2. Nope. Ag went from being +1 to 0. So its charge went down. So there's my reduction right there. All right, so let's now write our half reactions. So I'm just going to tell the story of what I figured out about who got oxidized again, Cu. So I'm just going to say, okay, once upon a time, Cu was 0, and then it became over here a +2. So it's really just like finding all your little charges, figuring out who got oxidized and reduced, and then just like writing it out in a little equation that only shows that one thing. We're just looking at copper. Now I just have to figure out which side to put these electrons on. Looks like there was a change of 2. But were they lost or gained? Well, oil rig oxidation is lost, so the 2 were lost, so I could put them over here to show them being lost, or I could just say, oh, +2 - 2, that equals 0. This side's 0. Got it. Let's do the reduction. So that was just, I'll just write what I saw Ag do. Ag was +1. And then over here, it became Ag0. And you can see I kind of leave like a blank spot in case I have to write it. So it looks like there was a change of 1 electron. So I'll write +1 electron. And I'm putting it on the left, either because I go, oh, reduction is gain. So I'll show it being added to the left to show it being gained. Or I can say the charge are supposed to add up to the same. This side's 0. So if this side I have this +1, this -1, this side equals 0. Voila. Okay, last thing is I'm just going to touch on balancing redox equations just for 1 minute. Other than that, we're going to skip this whole thing. But basically, you might have seen here that this reaction showed 2 electrons being lost. And then this one showed 1 electron being gained. And Mrs. Hoover, you said that if one loses 2, the other gains 2. And this one doesn't add up. So that's where you would go in and balance. You'd say, okay, well, there must have been 2 AGs that lost 2 electrons to make 2 AG zeros. So it's just like going in and putting numbers out in front that will balance it, just like we balanced back when we were balancing equations. It's not on the regions, so we're not going to do it, but I just do want you to be aware if you noticed you're like, hey, that's not adding up. This one lost 2, this one gained 2. You do need to know that however many one loses is the amount that the other one gains. So let's just write that instead of doing all this stuff. Let's just say that the number of lost electrons should equal the number of gained electrons. And there's this whole process of how you go in and you put 2 here, 2 here, 2 here, and it makes it all balance out so that one loses 2 electrons, the other one gains 2 electrons. But we're not going to do it. But what you do need to know is that however many one loses, the other one should gain that much because, again, we should show conservation of charge. Nothing is created or destroyed. It's just that these charged electrons moved over here.